will join. Sweet. Today is actually our last lecture of technical content. Wednesday will be our seated discussion, and then Friday will be our quiz. Plus, I'll try to have some of my grad students come in and talk to you all about the latest and greatest in the research world. Okay, so today we're going to start with a little recap, and we'll try to cover improvements in policy gradient, and then we'll talk about model-based out real quick. Okay, so to recap, we are trying to solve the record. Okay. We're trying to solve the reinforcement learning problem. So we're trying to find a policy to maximize the expected sum of rewards. So we're trying to find the parameters theta of a policy pi theta, which is a stochastic function from ST to AP, right? Such that when you act under pi theta, your sum of rewards or your discounted sum of rewards is as high as possible. And we said, okay, the way we're going to solve this problem is we're going to, sorry, folks. Okay, the way we're going to solve this problem, we start with imitation learning, and we said imitation learning. Someone gives you expert traces, and you want to get policies from those expert traces, but it has this compounding error problem. And we start talking about model free RL, and by model free RL, we said, okay, we're going to take this objective, which is the expected sum of rewards under a policy pi theta. And then we're going to do gradient ascent on this objective, right? So we're going to say, let's try to take the gradient and do ascent on theta according to this objective. Now, the tricky part with this ascent objective was that as opposed to normal supervised learning, the thing that depends on theta is the probability distribution, not the thing inside the expectation, right? And so basically the data distribution depends on theta, not F. And so we had to do some tricks together on it. The normal supervised learning looks like that, where the data doesn't depend on theta, only the thing inside. Like if you're maximizing log probability, the log probability depends on theta. In our case, the data distribution depends on theta. That's the difference. Supervised learning and the RL problem, right? Okay, so our challenge is that we can't normally in supervised learning, what we would have done is we would have said, okay, this gradient is just going to go all the way inside. So you're going to get an expectation with respect to gx of grad theta f theta of x, right? And you're going to estimate this with samples. So you're going to draw a bunch of samples from g of x. You're going to say x1, x2, x3. For each of them, you're going to evaluate grad theta f theta x1, grad theta f theta x2. Then you're going to like average them, and that's going to give you a gradient. You're going to move theta according to that average gradient, right? That's what supervised learning would do. You take a bunch of samples, you compute grad theta f theta xi, average them, and you take a step. Now, the tricky part is we need to find a way to represent this gradient also as an expectation, so I can compute it with samples and use auto differentiation and PyTorch and everything to implement. Right? So the important thing here is this grad theta, you don't have to compute it by hand. PyTorch does it for you, right? But you need to do it and you need to compute it as an average over a batch. And we're going to have to convert this gradient. So in this gradient, the important thing is I can't just take this inside because the thing that depends on theta is this guy. Right? So it's not as trivial to say how this thing is an expectation, right? And the expectations are the things that are easy to compute in code because you can just draw samples and average them. Okay, so that's where we were. We went through this derivation. So this derivation is trying to say we have the expected sum of rewards, let's call it J theta. And we're going to try and do gradient ascent on this expected sum of rewards, right? So we're going to say, let's take the gradient. And the gradient will move inside the integral, right? So this, you can, as long as there's some continuity, you can swap the gradient and an integral. And R doesn't depend on theta, only P theta tau depends on theta. And so we moved it into here, but this thing is not an expectation, right? So if you remember, an expectation looks something like this, right? And you can always write it as integral P theta x, f of x, d of x, dx, where P theta is a probability distribution. The problem with this expression is it's not a probability distribution. It is the gradient of a probability distribution, or a gradient of the probability density function. So I cannot express this as an expectation, which means I can't compute it with samples. So Does anyone remember how we got around it? What is the trick? We want to get it back to an expectation. So we have this thingy. We want to somehow express it in, in a form that looks kind of like this. How might we do that? Yeah. You multiply and nice. We multiply and divide. Right. So you multiply and divide by p theta tau, right? Um, and then you regroup terms. So you can think of if you ever had the integral px fx dx, right? You can regroup this thing to be this whole thing to be this, right? And then you get back to an expectation. If you have an expectation, which means you can compute it with samples, right? So the important thing we did was we grouped, we grouped this first term separately from these terms, right? And then we use the chain rule. So the chain rule says that if you have the gradient of log p theta with respect to theta, you can write this as the gradient of log p theta with respect to dp theta times dp theta with respect to d theta, right? This plain chain rule of calculus. And so what is the gradient of log? It is 1 over p theta. And the gradient of p theta, you can just write it as grad theta p theta x, right? So you can see that essentially what you'd often call the grad log p of x is essentially grad px divided by px. Right? So if I look at this expression over here, these two terms, the grad theta p theta tau divided by p theta tau is exactly the same as this chain rule that we worked out, right? So essentially all that we're doing is we're saying chain rule says grad theta log p theta tau is equal to 1 over p theta tau times grad theta p theta tau. Okay? Just from chain rule. And when we look at this grouping, this thing can just directly be written as grad theta log p theta tau. Right? So just chain rule. So now we can regroup these terms or rewrite these terms as p theta tau times grad theta log p theta tau r tau. But it's an expectation now. So the good thing is that it's an expectation. This thing is your p of x. This thing is your f of x. Right? And so if it's an expectation, I can compute it with samples. And so you rewrite it as an expectation. It gives you expectation under p theta tau of grad theta log p theta tau r tau. Right? So it's saying that you're going to sample trajectories. If you wanted to compute the gradient of this objective, you're going to sample trajectories from p theta tau, which means sample trajectories from your policy, yeah, in the world. You're going to compute this term, which will expand grad theta log p theta tau, multiplied by the rewards of a trajectory, and try to increase the likelihood of good trajectories and decrease the likelihood of bad. Right? So R tau tells you how good or bad a trajectory is. You're going to try and sample a bunch of trajectories and then weight them according to R tau, increase the likelihood of good, decrease the likelihood of bad. Repeat. So that's what the fundamental policy gradient algorithm is. But the important thing is we took this thing that didn't look like an expectation, we converted it back into an expectation. And with an expectation, you can just compute it in PyTorch with samples. So what we'll do is we'll again, I have to expand this a bit further, but the expectation, you can always sample a batch and then compute it as a average of a batch with Monte Carlo sampling, right? So whenever you have an expectation, you can always approximate it as the average over some samples drawn from that distribution. Okay, and this is often called the reinforced trick or vanilla policy gradient. But the question is, why is this called model free RL? Right? Like we still haven't, like this thing that I have is very abstract. Like what is tau? I only know states and actions in the world. How do I implement this in PyTorch, right? So let's unpack this a little further. So what we're going to do next is we're going to say p theta tau is like this kind of abstract weird entity. We're going to try and write this in terms of states and actions and policies and dynamics of the world. We're going to try and get into an expression we can implement in code. Right? Okay, so what what you're going to do is, if you look at the likelihood of a trajectory, right? If you remember how we sample a trajectory, you start by sampling an initial state. Then you sample an initial action from your initial policy. Then you transition to the next state in the world according to your transition dynamics. Then you sample the next action and you keep repeating. Right? So you have this sequential chain. You sample the first state, sample the first action, you transition in the world, you sample the next action, you transition in the world, you repeat. Right? So you can kind of think of it as like, essentially it's a chain. You're sampling in a chain. You're starting by sampling the first guy, then you're sampling the first action. Then those two together give you the first, or give you the next state. Then you sample the next action. Those two together give you the next state. Then you sample the next action and you repeat. Right? So given that, the likelihood of a trajectory, E theta tau. E theta tau is how likely was a trajectory tau, trajectory being a sequence of states, actions, states, actions, states, actions, with rewards. What is the likelihood of sampling a trajectory P theta tau when your policy is pi theta, and your dynamics are PSP plus 1 given ST and E, right? So it's just saying that imagine I had this sequential sampling process, right? Started from S0, then sample A0, then S1, then A1, then S2, then A2, right? You can always write the likelihood of a trajectory as the likelihood of sampling the first state, then the likelihood of sampling the first action. So you can write it as these product notation is a little confusing, but you can write it as P of S0 times P of A0 given S0 times P of S1 given S0 A0 times P of A1 given S1 times P of S2 given S1 A1 and so on. Right? So you can write as a product of initial state likelihood P of S0 times the likelihood of sampling a policy A0 given S0 times the likelihood of transitioning. And this likelihood is basically your policy by theta. Right? So this likelihood is again your policy by theta. So essentially you can say, whenever I have a sequential chain, the likelihood of a trajectory is a product of these three terms. If you haven't seen this notation pi before, it's just saying it's like the product from 0 to t minus 1. Okay. So whenever I, like in all the previous slides, whenever I wrote p theta tau, I just mean that product. Okay? And that product is in terms of states and actions that we know what they are in the world. Right? There's no abstract notion of a trajectory, it's states and actions in the world. Okay, so why is this important, right? Yeah.
I is policy is that the haven't heard the probability of options.
Yeah, probability over actions. Yeah, that's right. So each of these are probability distributions. But the important thing is, remember, we don't know this. We don't know what the likelihood of going to ST plus 1 given ST and AT in the world is because we don't know the model of the world. We can only draw samples from it, right? So what's going to happen is we're going to like replace all of our previous expressions with this guy, and it's going to give you something pretty cool. So if you remember from earlier, we want to get expectation under P theta tau of grad log P theta tau times R tau. We're gonna compute what log P theta tau is, right? So the log of a product of a bunch of terms is just the sum of the logs. So when I take the log of this thing, it separates into the log of the initial state distribution plus the sum of the log of the dynamics plus the log policy, right? So just imagine this term is just a product of a bunch of terms. It just becomes the sum of the log of each of those terms. And now what you're going to do is you're going to take the gradient of this expression. Right? So you're going to compute the gradient of this expression. Gradient of sum is sum of gradient. Right? So we're just going to hit each of these guys with a gradient. Yeah. So all we did is we said the likelihood of a trajectory is the product of likelihood of these individual terms. We're going to take the log becomes the sum. We're going to hit it with the gradient, right? Now the cool thing here is, if you look at the initial state distribution, it does not depend on your policy. So this is 0. If you look at the dynamics of the world, it does not depend on your policy. You don't determine how the world works. So this is 0, right? And so essentially, if you look at these terms, like two of the terms cancel out, and all that you have left is the last term, which is the sum of the log probabilities. The only term that depends on theta is this last guy, right? And so you can show that grad log p theta tau is just the sum of grad log probabilities along a trajectory. Because, and the way to intuitively think about this is your parameters, theta that you control, you can't control the world. You can only control your actions. Right? It's like a little philosophical. But if you think about like the things that you have control over in this like MDP, right? You only have control over how you choose these actions. And your actions determine how the world changes, but you can't change the physics of the world, right? And so these terms cancel out, and all you get is a sum over time of grad log pi theta of AT given ST. That's it. So this is called model free because I never need to know the model, right? I like took this model and I just canceled it out because I can't control it. So let's substitute it back into our previous expression, right? So our previous expression was expectation of trajectory sampled from p theta tau of grad theta log p theta tau is the gradient of the trajectory distribution times the sum of rewards for a trajectory. But we simplified this. We actually expanded this, right? And so we can rewrite this expression this. And so remember that grad theta log p theta tau, all the other terms canceled. So it just becomes t equal from 0 to t of grad theta log pi theta of AT given ST. So it's like you don't care about the dynamics of the world, you just care about the likelihoods of each individual state action pair. Right? And so that's what we're going to substitute in for the first term. And R tau is just the sum of rewards along a trajectory. Right? So this is grad theta log p theta tau. This is R tau. So it's the same expression as before. We just expanded it into something that we can implement. Right? And so the way you can kind of think about implementing this is you can just draw a bunch of samples. Right? So imagine you were in the world, you drew a bunch of samples, you run the policy, right? The way you run the policy is you sample an initial state, you sample initial action, you execute in the world, you sample a next action, execute in the world, repeat, right? So you draw a bunch of trajectories, you do a bunch of random stuff, right? According to your current policy pi theta. Whatever your neural net tells you to do, you just do it, you sample from it, right? And then what you do is you compute these two entities for every trajectory, for every single trajectory you have. Let's say this was a trajectory you sampled. Take individual tuples, right? Individual tuples of states and actions, let's say ST and AT. Okay. You're going to first start by computing, like stick ST and AT into your policy pi theta to get grad log pi theta AT given ST from PyTorch. Like, so imagine it as a Gaussian, right? You know pi theta AT given ST, you can get the log, you can get the log, you can get the gradient log, right? And so all you're going to do is take each of these terms, stick it through PyTorch to give you grad log, and sum them up. And then you're going to multiply it by the sum of rewards in every trajectory, right? So you're going to, for every single trajectory, you're going to compute a sum of the grad log pi theta of AT given ST along that whole trajectory. You're going to sum it up along the whole trajectory. Then you're going to sum up the rewards along the whole trajectory. Then you're going to multiply those two things together. Then you're going to average across many trajectories, right? So you can think of this as like happening for one trajectory, another trajectory, another trajectory, another trajectory, and then you average across all the trajectories. So remember, whenever you have an expectation, you can approximate it as the average over samples, right? So you're just going to sample a bunch of trajectories this way. You're going to compute this essentially sum of gradients, weight the sum of gradients by the sum of rewards, and then you're going to average over many trajectories. Okay, let's pause here for a second. Does that make sense? Is it confusing? What's confusing? Let's talk through it. Or let's think through it, right? Like which part is the confusion, and we'll double click.
I mean, identification. somewhat tricky just to lag this, but like the concepts make sense.
Okay. Any other questions? Things that the notation is a lot because I try to be precise here because it's just like otherwise it's like shorthand and you don't know what's happening. But essentially don't be too afraid. Like I always find this thing the most terrifying. But essentially all that it's saying is that you're sampling a sequence. You're just sampling things in order. Yeah.
Why is it summing over?
Typo. That should be T prime. The reason I have them as T prime is because they have like, it's like whole sums. So you sum up the grad log over the whole trajectory, you sum up the reward over the whole trajectory, and you multiply them together. Yeah, yeah. It is important because in the next couple of slides, there's a version where it's not the whole summations multiplied, it's like a nested sum. Okay, so let's keep going. So intuitively, right? This looks, all that policy gradient means is increase the likelihood of good stuff, decrease the likelihood of bad stuff. Right? And so imagine you had three different trajectories, R equal to 30, R equal to 100, R equal to -10. You're going to compute the grad log pi's for each of these sub-steps. And then you're going to weight all of the ones in this trajectory by 100, all of the ones in this trajectory by 30, all of the ones in this trajectory by -10. And so the stuff that is in this, all the grad logs which are in this trajectory will go up. These will go down. This will go up only a little bit. Okay, so if I just look at this intuitive way of thinking about it, right? You sum up the grad log probabilities for the whole trajectory and then weight it by 100. Like, why might that be a problem? Like, what could go wrong with that? So the problem is often what you call a credit assignment problem. So imagine you did a bunch of random stuff in life, okay? And then somehow by the like stroke of luck, you like got lucky and you like succeed. You took a bunch of really poor decisions and then somehow you got lucky and you succeeded. What's going to happen is it's going to upweight all of those poor decisions that you took earlier. It's going to assign credit to all of those when it shouldn't have, right? And so the challenge in policy gradient is that you are lumping together the decisions across a bunch of stuff, right? And you're saying that like, I don't know which of the stuff was good. The only way to figure out which of the stuff was good is to like pair different stuff together. Like take decision A with decision B and with decision C and see which one is better. And then you can assign credit to was it A that is good or B that is good or C that is good. And so the tricky thing in sequential decision making is in this whole trajectory, I don't know if this initial part was good or bad. I just know the outcome of the whole trajectory. And if I only know the outcome of the whole trajectory, maybe I'm upweighting stuff that is inherently pretty bad. Right? And so it's far from optimal. And so this is often called variance in policy gradient. Like one of the big challenges in policy gradient is the problem of variance in the sense that you need a lot of trajectories to get a pretty accurate estimate of the gradient, right? Because you can kind of think of it as like, if every decision is paired with a bunch of other random decisions, in order to get a pretty accurate estimate of which things were good, you need a ton of samples. So if you ever look at any like RL algorithms for LLMs or for robots in simulation, they're often trained with these huge batch sizes, like millions of things so that you can like reduce the variance of decisions. Okay, so this algorithm is called reinforce. It boils down to the following. You start by sampling trajectories. You compute grad log pi, sum it up. You compute R, sum it up, multiply those two things for every single trajectory, and then average across the trajectories. You get a gradient on your objective with respect to theta. Right? So if your imaginary parameters were an n by 1 vector, this is another n by 1 vector. You take a step on your parameters, you do gradient descent, and then you sample again, right? So the important thing about this algorithm as currently constructed is that it is what you'd call an on-policy algorithm. You always have to take samples from the latest policy. Like in order to accurately compute the gradient, I always have to draw samples from the latest policy, which means that I always have to keep redrawing samples, and everything I did in the past was useless. And so one of the challenges with a non-policy algorithm is like you're wasting so much data, right? You're like saying, I'm going to like learn with my latest batch of trajectories, but everything in the past was useless, right? So essentially I run this once, I compute the gradient, then I throw those things away. And I run it again, compute the gradient, and I throw those things away. So that's what an on-policy algorithm would be. And a non-policy algorithm generally is like performant in the large data regime, but it struggles with small amounts of data because you're wasting so much data. Okay, and if we connect this back to supervised learning, if you remember what supervised learning was, supervised learning was saying this to maximum likelihood. Let's sample X and Y from your data distribution. And let's say you have log p theta of Y given X. You want to maximize the likelihood of producing Y at X. Okay? And so remember, we can move, when you take the gradient here, you can move the gradient inside. And so we'll get expectation of X and Y from your data of grad log p of Y given X. Right? So you just compute grad log p for everything in your data, average it. Now the difference in reinforcement learning is you you still have grad log pi, but you always take it under the latest batch of samples, not under a stationary data set. And you're summing up the reward and weighting things. Right? So weighted things that are good, increase their likelihood, and downweight things that are bad. But they look very similar in many ways. The other important thing in reinforcement learning is that you are not separating the decisions across different time steps. Right? In imitation learning, what we did is we took all the time steps, we jumbled them up, we pretended it wasn't a sequence. But in reinforcement learning, you're explicitly tying together the outcomes across multiple time steps. Right? So remember, I'm actually computing this whole sum and this whole sum. And so I'm not allowing it to have compounding error because I'm taking into account how one action affects the next, affects the next, affects the next. So typically RL won't have compounding error in the same way that supervised learning does. It has other problems, but not compounding error. Alrighty, that was the recap. So, any questions? If you ever wanna to go back to this algorithm, just think of it as I find this one the easiest one to think about. Increase the good stuff, decrease the bad stuff. Grad log pi is telling you what stuff to increase, or grad log pi is telling you to increase, and R is telling you what stuff to. Okay, so how are we doing on time? Okay, we only have 20 minutes. So I am going to rush through the next part and just give you the vibes. Don't worry about the math, right? Um, the, the challenge with policy gradient, as we just talked about, is that all of the decisions are coupled. Right? If all the decisions are coupled, you have what you call a single sample estimate, right? So imagine that you took a single trajectory, you computed the grad log pi for that single trajectory, and you're like weighting it by the reward. It's like you're beholden to like let's imagine you either took a bunch of really good decisions, but you took one bad decision at the end. You're going to like downweight all of the good decisions, or vice versa, right? And so if I had many more samples, like it would average out those lucky effects. But in policy gradient, as you're currently constructing it, it's a single sample estimate. So you just compute this thing for one trajectory at a time, then you average it. And so this gives you a variance problem. And what you really want is something that looks more like this. What you really want is to say, like at any one point, I want to say, let me try many different things and let me see which of those things was good. Right? And so you want to average your outcomes over many different trials. The problem is that in the world, you can't just like magically teleport to here. Right? So you can never come back to the same place. And so a lot of what reinforcement learning algorithm work is about is trying to approximate this guy rather than that guy. Okay, so we're gonna try a bunch of things to reduce variance, right? But the first thing is pretty easy to understand. Like Evan was just asking about, um, the uh, the indexing is pretty important. So in the current version of the indexing, you can kind of think of it this way. You're summing up the reward for a full trajectory. You're summing up the grad log pi for a full trajectory, and then you're averaging it over many trajectories, right? But one thing is it's what this is doing is it's coupling the grad log pi's of the future with the past, right? So it's saying that like I'm gonna I'm gonna use the rewards of the past few trajectories to also weight the outcomes of things in the future. Right? So because I'm summing up the whole trajectory and the whole trajectory. But because we're in a Markovian world, in the future does depend on the past condition on the present, right? And so the future is independent of the past condition in the present. One thing you can do to reduce variance is just like ignore the past, right? And so you can kind of think of it as like, well, the past is the past. I can't control it. I can only control what happens in the future, right? And so I don't need to worry about weighting the decisions of the future with the past once I'm conditioned on the present, right? And so one easy way to think about it is like you're like wiggling this rope, right? And you're trying to like reduce the variance and wiggling of this rope. And right now what's happening is you're hitching yourself to all your past mistakes, but you want to just cut it on your current state. You're trying to find what is the best thing to do given that I'm already here. Right? And so the first thing that people do is that rather than summing up the whole trajectory, you weight grad log pi's only by the sum of rewards in the future. And so if you remember LQR, you guys did LQR, right? With SIT. There's this concept called reward to go, return to go, cost to go, right? Essentially what we're going to do is we're going to say we're going to weight our grad log probabilities by only the things in the future, right? So one way to think about it is take this grad log probability, the first one, and then multiply it by all the rewards in the future. Then take the second one and multiply it by the rewards from there till the future, but not the first one. And then the next one, you will multiply it by the rewards from there to the future, but not the first two, right? And so you only care about rewards in the future because your decisions can only impact the future, not the past. Right? And so my decision at this time 50 will never change what I did here. We can only change the future. And so that's the first thing we do. We're going to just like ignore things in the past because I can't change them. Okay, so that's the first idea. The second idea is this idea called variance reduction via a baseline. And so the easy way to think about it is that imagine you took all your trajectories and you like scaled them by a constant, right? So imagine your rewards were this, that, and that. If you scale them up by a constant, you added a constant to everything, right? It really shouldn't change your gradient. But what happens is that it does because the scale of rewards, you could have some states where the rewards are 10,000 and some states where the rewards are 10, right? And so what we're going to do instead is we're going to try and recenter all the rewards. And so I'm going to skip through this slide, a little confusing without more context. But the idea behind the baseline is that imagine that you had one state where the rewards were like 100 and 102 and 105. Another state where the rewards were like -10, -8, -6, right? What you care about is the difference between different actions at the same state, but you don't care about the scale between the states, right? And so what we're going to try and do is we're going to try and like center. We're going to try and say this is the future rewards, but you only care about the relative comparison between different trajectories at that state. So you're going to try and center it so that all of the states are on the same scale. And by putting them on the same scale, you're going to reduce the variance, right? And there's a lot of nice theory about this. We will not be able to cover it in 10 minutes, but you should take my RL class if you want to learn about it. And what people often do to compute this centering function is that they have a neural net learn the average reward at a particular state. And so this is often what you'd call a value function, right? So if you ever see value function or an advantage, like this comes up in lots of RL literature, but essentially what the simplest way to understand it is your returns are all over the place in terms of scale. You're just trying to average the scale by computing the mean reward at that state across many different trajectories and centering everything. So that's our second idea of variance reduction. And then the third idea, which we'll cover in our seated discussion on Wednesday, is this idea called proximal policy optimization, PPO, stuff that does all your LLMs and your humanoid robots jumping around. A lot of them are powered by PPO. And the idea behind PPO is that RL is kind of like walking on a tightrope. And what I mean by that is like you can think of on policy RL as this process of collect data, compute the gradient, right? Gradient moves you to some new theta, and then you collect data with this new theta again, right? Now, what happens is if you take a step that is too big, and so it's kind of like if you, this is like an analogy here, but if you take a step that's too big, you kind of fall off a cliff. And if you fall off a cliff, then your data sucks and you never get better, right? And so in normal supervised learning, if you fell off the cliff, the data remains the same, you can keep coming down. But in reinforcement learning, it's like the thing that you're doing updates on is the thing that's collecting the data in the first place. And so if you like start, if you take too big a step, imagine you had some optimization function, right? And you were like right here, you want to reach the top of the mountain, you take too big a step, you like fall to your death, right? And in reinforcement learning, it's much harder to recover from the death because the data starts sucking. Whereas in supervised learning, the data remains stationary. And so a big idea in reinforcement learning that's been really powerful is to like restrict how much the policy changes. You never let it take a big enough step to fall off the cliff. And so the simple idea in PPO is to just have like a little clipping term, which says that don't let the policy change a lot. So we'll cover it in more detail on Wednesday. You should read the paper. But the intuitive way to think about it is you want to clip the change between pi theta and pi theta old, which means that between your current, and what you're going to, never let it change a lot. And if you don't let it change a lot, then you never fall off the cliff and can't recover. Okay, so for the sake of time, let's keep going. Some examples here. I think these are always fun. Is like, this is back in 2015, learning to walk with a humanoid. You can see that this is just like a version of this PPO-ish algorithm that's able to learn in a couple thousand trials. So these are fun, but then you can apply them to other stuff. So this was, I think, Dota 2, where they were able to achieve superhuman performance, and you can apply it to robotics problems too, right? Like rotating this Rubik's Cube and so on. All the same algorithm. The cool thing is it's like the same algorithm with very few changes. The other nice thing is people use it for LLMs. There's some new variants called GRPO, but GRPO is like not that different from PPO. It's the same thing. But it kind of powers a lot of your LLMs. And you can also get it to work on real robots in the sense you can get the learning to happen in the real robots. So for instance, here is an example called Walk in the Park, where you can teach a robot dog to walk from scratch in 20 minutes in the hills of Berkeley. And yeah, that's what we're going to cover for model free RL. But the important thing in model free RL is remember that model free RL is essentially trial and error, draw a bunch of samples, weight the good stuff more, the bad stuff less. Just doing that leads to a variance problem. Like your decisions are coupled with all your other decisions. You don't know where to assign credit. And so a lot of the research in policy gradient is just reducing variance. Okay. I'm going to rush because I only have 9 minutes. And so we'll try to cover a little bit of model-based RL before we run out of time. Okay, so the idea of model-based RL is that in control and those kinds of things, we assume that we knew the model of the world. We knew the A matrix and the B matrix in LQR. You knew the dynamics model in your MPC project. You had a simulator, right? But model-based RL, we're not going to assume that we have access to the simulator. We're only going to assume we're only going to assume that we have access to the data. We can still only sample from the environment. But as opposed to model free RL, model free RL's goal is going to be to learn the policy directly. Model-based RL's goal is going to be to learn an approximate model of the dynamics of the world and then do like decision making in that approximate dynamics of the world. So it's going to try and use the data to learn how the world works approximately, and then it's going to try and make decisions in that approximate model of the world. Right? And so the idea behind model-based RL is we're going to learn a surrogate model of the dynamics of the world. We're going to learn a surrogate model of this unknown function. Let's call it p hat, right? And then we are going to like pretend that p hat was the real world. And we're going to say, I don't know the real world, but I'm going to get data from the real world. I'm going to learn a surrogate. And from that surrogate, I'm going to make decisions. Because I did all this work on control, I know how to do decision making in if I knew p, right? And so I'm going to do the same thing for p hat. And so you can kind of think of model-based RL as very connected to control. It is control under a learned model. Okay. So you're going to try and break it into two stages, which you sometimes interleave. First stage is learning a model. The second stage is making decisions in that model, pretending it is the real world. Okay, so there's two parts to it, model learning. And typically model learning is going to be supervised learning, right? So you're going to say that I'm going to get sequences of states, actions, next states, and I'm going to do maximum likelihood. I'm going to do supervised learning. I'm going to do the same thing we did in imitation learning, but I'm going to say I'm going to maximize the log likelihood of producing S prime given S and A when I sample S, A, and S prime from my environment. Okay. So all this is saying is that I'm going to like try and learn a model of the world that best explains the data that I saw as a supervised learning problem. And the next thing I'm going to do is I'm going to do what you call planning, right? It's a little confusing because it's not the same thing as the like um, roadmap search and lazy A star and those kinds of things that you did. This is closer to control, right? So when we say planning in model-based RL, it kind of means control. Like you're trying to find a sequence of actions or a policy that minimizes cost or maximizes reward in the approximate model of the world P hat, right? So I'm going to start by trying to learn an approximate model of the world P hat. Then I'm going to try and make decisions in that P hat, which maximize reward. Then I'm going to play those decisions in the real world in P. So I don't know P. I'm going to get samples from P. Right? Samples are going to be used to train P hat. I'm going to figure out how to make best decisions in P hat, play those decisions in the world, get more samples, repeat. So compared to model-free RL, in model-free RL, what we did is we said, okay, we're going to like go from P to a bunch of samples. We're going to upweight and downweight those samples, directly update the policy. There's no model in between. And model-based RL, what we're going to do is we'll say, let's try and approximate a model in between and make decisions in that model. Okay, so the general template of a model-based algorithm, you start by collecting data. You're then going to try and learn a model with supervised learning. Then you're going to try and do planning, decision-making control inside that model. Then you're going to go back to data collection and you're going to repeat, right? You're going to just go data collection, model learning, planning, data collection, model learning, planning. And so there are a few different variants, and we certainly won't cover 3 of them in 5 minutes. But let's kind of touch on them a little bit, right? So the first and simplest version of doing model-based startup is this idea called random shooting. And so do you guys cover random shooting in control? No? Okay. Random shooting is stupid, but essentially you're going to start by learning your model just with maximum likelihood. You're going to try and say, if I got an S and A, can I predict S prime with as high likelihood as possible? Regression, right? Regression, classification, whatever. And then I want to do decision making. And the easiest way to do decision making is to say, I'm going to sample from any state. I'm going to sample a bunch of random actions. I'm going to choose the ones that have the highest reward. That's it, and run them. Right. So the first idea of random shooting is to say, I'm just going to do a bunch of randoms. I'm going to take a bunch of random samples. I'm going to compute the sum of the rewards. I'm going to see which one had the highest sum of rewards. I'm just going to play those actions open loop. Right. Okay, so this is the one that had the highest sum of rewards, and I'm just going to execute these actions. Now, the challenge with running things open loop is what? Compounding error, right? It tends to drift. And so if I'm going to run things open loop, I'm going to have compounding error. It's going to drift. And so we're going to use the same trick that we use in your control module. We're going to just do MPC, right? We're going to run it once. You're going to replan, and you're going to run it again. You're going to replan. You're going to run it again. You're going to replan, right? And so the first variant of model-based RL is that you're going to do MPC in the learned model, right? And so you're going to take a bunch of random samples. You're going to pick the best one. You're going to execute it once. You're going to take a bunch of samples, pick the best one. You're going to execute it once. Repeat. Okay. But the important thing is that you're doing this in the learned model, not the true model. Okay, and so the procedure is pretty simple. It says plan with random shooting from ST, execute the first action, reach ST plus 1, plan with random shooting again. So um, this kind of thing does work in practice. Doesn't work amazing, but it does work on a real robot. It does work in simulation. Um, but what's the challenge with, like, why is this not good? Well, it's not good because this is like a terrible way to search through a high dimensional space. You're just like doing random stuff, right? It's like, imagine that you only had reward here. You're like searching for a needle in a haystack, right? And so the next method we're gonna rush through is is this idea called MPPI. And what it's trying to deal with is this needle in a haystack problem. It's trying to say you're trying to do random samples. You're trying to shoot darts at an infinitely large dartboard until you like accidentally hit the goal, right? And so this is not a particularly good way to search the world, random shooting. And so what some folks kind of came up with is this idea of reweighting your sampling distribution according to what you care about. And so the idea here is if you do random shooting, you just draw a bunch of random samples, IID, all the time. You're always drawing them from the same distribution, let's say a uniform distribution. But let's say I really care about like things in a particular neighborhood, right? So I really care about things in like this neighborhood. Why am I wasting my samples here and here and here and here, right? And so the idea behind MPPI or model predicted path integral is just to say, let's try and inform how we're sampling according to which things have good reward, right? So the idea behind MPPI is that the first time you do things, maybe you draw samples according to that distribution. But the next time I draw samples, it shouldn't be according to the same thing. It should be focused around things that were high reward, right? And so what you're going to do is you're going to iteratively reweight your sampling distribution according to the rewards of the things you got in the previous round, right? And so you can kind of think of it as you start by sampling a bunch of action sequences, you run them through the world, sample actions, you run them through the world, and then you upweight things that have high reward, right? So you can say, I'm going to take the exponential sum of rewards. So let's say, um, let's say trajectories at the top had low reward, trajectories at the bottom had low reward, the things around here had high reward. The next time you're going to sample for planning, you're just going to do it for something that is reweighted to be high around the things that were like in the middle, right? And so the whole point is I'm searching for a needle in a haystack, but I'm going to be searching for it in a smaller space. I'm not going to be wasting samples everywhere, right? And so the idea behind MPPI is to just iteratively reweight your distribution to be closer to the things that have high reward. Okay, so this is what MPPI is. Nothing really changes. You still learn your model with supervised learning. You plan with MPPI, but so rather than just doing draw a bunch of samples, pick the best one, you do the iterative process where you draw a bunch of samples, reweight the stuff that is good reward, and draw a bunch of samples again, reweight the stuff that is good reward, repeat, 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 before playing an act, right? And so the idea behind MPPI is that you have like, it's a better search algorithm than random shooting. Okay, that's it, right? So you're just going to reweight stuff that is high reward. Does it work? It works super well, actually. Here's an example from Byron's group, actually, where they're drifting with MPPI. So they learned the model of the world with a neural net, and then they planned this model at high speed to do drifting. So that's pretty awesome. No simulator, just real data here. You can also apply this to manipulation. So here's an example of some things you can learn in just 20 minutes of real data. You can learn to do like in-hand reorientation of objects. Or 2 hours of data, not 20 minutes. Okay, so maybe I'll touch really quickly on the last part. But it's important to think about why learned models are not the same as known simulators, right? The important problem with learned models is the same problem you have with imitation learning, right? Like imagine you had a learned model and you trained it on like this training data set. Let's say you made a small mistake in the learned model. Now you're out of distribution, which means the next thing will have a bigger mistake, which means the next thing will have a bigger mistake, right? And so you still train this sequential problem as a one-step problem. And so the same problems you have in imitation learning, you'll have in model-based startup. in the sense that you have your true rollout, but because you have small errors in the model, and you're sampling by like taking one step at a time, putting it back into the model, you'll have these kinds of compounding error deviations from the true trajectories. And so essentially errors in your prediction go to OOD next state, and this kind of leads to bad decisions. And why does this matter? Well, if you have decisions that were actually bad, they could lead to things that are good, and things that were actually good, they could lead to things that are bad. So if you look at these video models, like things from, um, NVIDIA or Google and stuff, sometimes they hallucinate. You'll see them hallucinating, like picking up of a cup. It's often the same issue. Okay, so the model becomes bad in all of these states. And so often what used to happen at least is that if you go 5 or 10 steps in the future, your model starts deviating from reality. And if you like plan on that, it gives you pretty suboptimal decisions. And so the key here is you want to measure and deal with uncertainty. And so the figure to think about is basically if I was able to estimate that I've gone OOD here, and I'm able to like downweight it, then I'm not going to make decisions that hallucinated things, right? And so the key idea in uncertainty-driven model-based RL is to measure a notion of like how OOD am I? And if I know how out of distribution I am, I can downweight those decisions. Right? And so we won't have time to figure out how exactly to do it, but the way to kind of think about it is when you're doing planning, if you had a measure of your uncertainty, you just penalize decisions by saying that don't trust anything where I'm highly uncertain. So like never take an action that leads me to a highly uncertain state. Right? And so this is often called pessimism, right? Pessimistic planning. And that's going to kind of keep you in the realm of things that are well known. So these ideas were kind of used again in a lot of these robotic settings to stay a little bit pessimistic. Okay, so that is all of the technical material in our class. We'll have some fun discussions on Wednesday, and we'll have a quiz and some research presentations on Friday. All right, thank you.